Hey, gang, I thought you might like to take a look at an example of a telescoping series, or another example, because I know we did a couple in class. And what I did was I wrote out the first several terms of the series where it's unsimplified, because I thought what we could do is take a look at the corresponding sequence of partial sums. So we can take a look at this right now, and I think you can see the terms are going to collapse on themselves. It looks like 1/4 here and here are going to go, 1/5 are going to go, and so on. And here's what the sequence of partial sums look like. I can actually rearrange these terms, I guess. I can write like this, huh? Okay, the third partial sum okay, now here the 1/4 are actually going to cancel. We're going to get a 1/2 and a 1/3 minus 1/5 minus 1/6. Okay. I think we see a bit of a pattern emerging, huh? We got a 1/2 plus a 1/3, and then minus a 1/4 minus a 1/5. Then the 1/2, 1/3 again, minus 1/5 minus 1/6. The fourth partial sum, which you can verify, is going to wind up being 1/2 plus 1/3 minus 1/6 minus 1/7. Fifth partial sum, so it looks like the 1/2 and the 1/3 are stationary, whereas the third and the fourth fractions, look at those they're getting smaller and smaller. In fact, the further we go out, the more these tend towards 0. If we were going to come up with a general term for this sequence of partial sums, what would it be? Let's see. Well, we know we're going to have the 1/2 and the 1/3 minus these other fractions with 1 in the numerator, right? But what would the denominators be? Let's see, maybe if we can use the subscripts here as a clue. Look at this one, for example, right? We've got a 5 here, and down here we've got a 7 and an 8. I would need to add 2 to the 5 to get a 7, 3 to the 5 to get an 8. So maybe we write like this, n plus 2 down here and an n plus 3. You think that'll work? Let's see if it'll work for the other ones. When n is equal to 4, down here I'm going to have 4 plus 2 is 6. There it is. And 4 plus 3 is 7. There it is. Okay, so far so good. For the 3, right? If we take n is equal to this 3 right here, 3 plus 2 is 5, right there. 3 plus 3 is 6. Okay, so you see it's working. For n is equal to 2 right here, we're going to have 2 plus 2 is 4. 2 plus 3 is 5. But what about this one? Well, maybe we write it like this. Let's write it as 1/2 plus 1/3 minus 1/3 minus 1/4. Right? Because that's the same thing as this. And then it fits the pattern that we established down here. Okay, when n is equal to 1, we would have a 3 and a 4. And that's exactly what we have here, a 3 and a 4. So here's our sequence of, here's our sequence of partial sums with the fancy notation. Here's the general term right here. Okay, and notice that the limit is going to equal 1/2 plus 1/3 minus 0 minus 0. And 1/2 plus a 1/3 is what's that, 5/6. Therefore, we say, since the sequence of partial sums converges to the number 5/6, We can go all the way back up here and say that the infinite series converges to the same number. Okay, what do you think of that? Okay, now here's another example. And the first several terms of this, if we write out the first several terms, are going to look like as follows. So this is a little bit different. The examples that we've seen before, we were using rational expressions, but I mean, you don't have to use those. Okay. Now, the first partial sum is the square root of 5 minus the square root of 4. Second partial sum so on. Okay, here, let's see, the square root of 5's cancel again. The 6's are out. Looks like we're going to have the square root of 7 minus the square root of 4. Okay, in a similar way, the fourth partial sum okay, and I bet you detect a pattern, gang. Can we figure out the general term? What would the general term be? What do you think? Well, let's see. If we go off of the subscripts like we did before, for example, first of all, I think everybody sees that we've got minus the square root of 4 on this, okay? And if you look at the terms in the first terms, right, notice that this one, like what would I have to do to the subscript 4 here to get the 8 here? I would have to add 4 to it, okay? Does that hold for this one? Okay, subscript is 3. If I add 4 to that, I'll get 7. Over here, the subscript is 2. If I add 4 to it, I will get 6. So it does hold. I think we're safe in saying then that the general term should be square root of n plus 4 minus the square root of 4. Okay, so our sequence of partial sums has the general term like that. And if we take the limit of our sequence of partial sums, at least the general term, this is actually going to equal infinity. Okay, so here's an example of a telescoping series that actually diverges. Okay, so since the sequence of partial sums diverges to infinity, then the original series up here, we say, diverges as well. Okay, so a couple of examples of telescoping series, and I think this is a good example to show us that even though the terms are going to be collapsing, that doesn't necessarily mean that the series is going to converge.